Good day to all of you students. Starting the second semester of your school year, we are now stepping forward to another set of valuable lessons for you to know. With that, we shall start our first topic in the subject Math 100. The first topic is asked for understand and dwell deeper on mathematics itself, or rather, its history. What is the history of mathematics? And do you think that the history of mathematics is important? We will find the answers later on. And after that, the next topic will be about the Babylonian numeral system, which is the first numeral system topic that you will encounter throughout this subject. So now let us start. Going to the introduction. Studying mathematics is essential. The word essential specifies how powerful the concept of mathematics is for the world. There are a lot of reasons, uses, and importance of the mathematics itself. Some of this is that it sharpens critical thinking, enhances problem-solving skills, and contributes the foundation for advancements in science and technology. And to add more of that, mathematics is not just about numbers as it teaches discipline, logic, and the ability to think in different ways, or example, in abstract ways. Among the foundational topics in mathematics is the numeral system, which is a method of representing numbers. The Babylonian numeral system, which is will be specifying in this lesson, is an example of a basic system that has been influenced later in numerical systems, a stepping stone for advanced mathematical exploration. Let us proceed to the objectives, of course. In general, the objectives for the topic to be learned is to first understand mathematics, explain what mathematics is and why is it important. Aside from that is to know the branches of mathematics, identifying the main parts of mathematics like algebra, geometry, and statistics. After that is to learn the history of mathematics while discovering how the mathematics started and how it has changed over time until now. Next is understand why mathematics is important. Next is to learn and explore Babylonian numeral system, which is another topic or lesson, and we will explain the Babylonian basic system and why is it important and relevant.
Good day everyone, I am Kylie Marin Tulin and I am here to discuss what is mathematics and its history of origin, especially in the Babylonian numerical system. And we all can agree that math is one of the hardest and a challenging subject of all. And I know some of us think and ask the same question. What is mathematics? Mathematics is like a universal language that helps us understand the world around us. It's about patterns, relationships, and structures, whether in numbers, shape, or even the way things change over time. It's a powerful tool for solving problems, from building bridges to understanding the universe. We use math daily for tasks like managing money and time and navigating using maps or GPS. It's more than just calculations. It's a powerful tool for exploring and solving complex problems. Now let's discuss the branches of mathematics. Mathematics is a vast field divided into two main branches: pure mathematics and applied mathematics. Let's explore each. Pure mathematics, the world of abstract ideas. Pure mathematics focuses on exploring fundamental mathematical concepts and structures without immediate concern for practical applications. Think of it as a building the fundamental blocks upon which applied mathematics is built. Here are some key areas. First is algebra. This isn't just about solving equations. Algebra is the study of mathematical symbols and the rules for manipulating them. It's the language of mathematics, allowing us to represent and solve complex problems in a concise way. Think of it as a grammar of math. Second, the geometry. Geometry deals with shapes, their sizes, and their properties in space. It's not just about triangles or circles. It explores higher dimensional spaces and complex complex shapes with fascinating properties. The third one is calculus. Calculus is the mathematics of change. It provides tools to understand and model how things change over time or in relation to other variables. Derivatives help us understand in instantaneous rates of change, while integrals help us calculate accumulated quantities. And the fourth one is number theory. This branch delves into the properties of integers, whole numbers, and prime numbers. Numbers only divisible by 1 and themselves. It explores patterns and relationships within these numbers, leading to some of the most profound and challenging problems in mathematics. Then fifth is topology. Fifth is topology. Topology studies shapes and spaces, but its focuses on properties that remain unchanged even when the shapes are stretched, twisted, or bent, as long as they can turn or glued. Think of it as studying shapes like rubber sheets properties. The second branch of mathematics is applied mathematics. It is putting math to work. Applied mathematics takes the theoretical concept from pure mathematics and uses them to solve real-world problems across various fields. It's about applying mathematical tools to practical situations. Here are some examples. Statistics. Statistics is all about collecting, analyzing, and interpreting data. It helps us understand patterns, make predictions, and draw conclusions from informations. Second is operation research. This branch focuses on optimizing process and decision making. It uses mathematical models to improve efficiency in areas like logistics or supply chain management and resource allocation. Third one is mathematical physics. This fascinating area uses mathematical tools to describe and understand physical phenomena. It bridges the gap between the abstract world of mathematics and the concrete world of physics. Then the last one is cryptography. Cryptography uses mathematical techniques to secure communication and protect information. It's essential for online security and protecting sensitive data. These two branches provides a clearer understanding of the two main branches of mathematics and some of their key areas. Remember, these branches interconnected and many mathematical concepts find applications in multiple fields. History or brief history of the evolution of mathematics. Let's take a trip back into time to see how math evolved. Historical origins. Earliest records is the evidence of mathematical concepts dates back to around 3000 BCE in ancient Mesopotamia and Egypt, including basic arithmetic, geometry, and algebra. Imagine, way back around 3000 BCE, that's when people in Mesopotamia and Egypt started using math. They figured out how to count, measure, and even solve simple problems. Think basic addition, subtraction, and finding the area of a field. Basically, this is the beginning where people learn math. Second is the Greek contributions. Ancient Greek mathematicians like Euclid and Pythagoras developed deductive reasoning and axiomatic systems. So basically, they were like math superstars. Of course, Euclid, who wrote a book called Elements that's still used today to learn geometry. And here, Pythagoras, who figured out the famous rule about triangles. The Greeks were all about proving things with logic and reasons. Here comes next the medieval advancements. Islamic scholars preserved and expanded mathematical knowledge during the Middle Ages, introducing algebra from the Arabic word algebra and trigonometry. So, during the Middle Ages, Islamic scholars kept math alive and well. They were brilliant. They invented algebra, which is all about using letters to represent numbers. They also figured out trigonometry, which help us measure angles and distances. And here comes the modern era. Mathematics evolved significantly during the 17th century, with calculus developed independently by Isaac Newton and Gottfried Wilhelm Leibniz. Now, fast forward to the 17th century, that's when calculus came about. So, it's a super powerful tool that helps us understand change and motion. Two geniuses, Isaac Newton and Gottfried Leibniz figured it out almost at the same time. So, from the basic counting to complex calculus, math has been a journey of discovery. It's amazing how people from different times and places have contributed this fascinating subject. Let's talk about the prehistoric era. Imagine life 35,000 years ago. People were hunter-gatherers living in small groups. They needed to keep track of things, how many animals they hunted, how many people were their tribe, and how much food they had. The origins of mathematics are found in counting and measuring. So, they didn't have calculators or fancy tools back then. Instead, they used their fingers, sticks, and stones. Think of it like a primitive abacus. They might have made marks on bones or rocks to keep count. So there are evidence. The Ishangu bone. The Ishangu bone discovered in Africa has notches that suggest early arithmetic or calendar tracking. Early humans likely used to tally marks to record quantities for trade or resource. So, resource management. So, the Ishangu bone is one of the coolest discoveries in this time. So, it's about 20,000 years old and was found in Africa. It has notches carved into it, and some people believe it's a very early example of arithmetic or even a calendar. So, early humans used tally or it is another common way to keep track of things was to use tally marks. So, think of it, those lines you make when you're counting something, these marks were used for trading, sharing food, or even just remembering how many days had passed. So, the importance of this era is it has laid the foundation for the development of arithmetic and basic geometry. So, this era might seem simple, but it's where the very basic ideas of numbers and counting were born. It laid the groundwork for all the amazing math we know today. So, without those early efforts, we wouldn't have the complex math that helps us build buildings and explore spaces and understand the universe. Now let's talk about the ancient civilization. This period saw mathematics develop independently across multiple civilizations. This period is so significant because it shows how humans across different cultures were naturally drawn to the beauty and power of mathematics. They developed their own systems to solve problems, measure things, and understand the world around them. So, here in ancient civilization, under ang Babylonian mathematics. So, Babylonian mathematics is 3000 BCE to 300 BCE. So, early algebra, solutions to quadratic equations and systems of equations. So, Babylonian contributes in astronomy. So, Babylonian mathematics excelled in algebra, solving quadratic equations and systems of equations. Their detailed astronomical observation led to advancements in calendars and eclipse prediction, significantly influencing later civilization. Then the second is Egyptian mathematics is also under in ancient civilization. So, practical geometry for land measurement or surveying land. The Rhind mathematical papyrus provided instructions for solving linear equations and calculating areas. So, Egyptian mathematics prioritized practical geometry for land measurement and construction, as evidenced by the Rhind papyrus, which details methods for solving linear equations and calculating areas. So, next time if you see a pyramid or think about the geometry of a building, remember the ancient Egyptians. Their practical math skills were essential for creating a thriving civilization. The third one is Greek mathematics is also under ancient civilization. So, shifted focus to logical deduction and proofs. So, nadiri sila Pythagoras, Euclid, Archimedes, and so on. So, Pythagoras' relationship between sides of right triangles is Pythagorean theorem. So, Euclid wrote elements as a systematic presentation of geometry. Archimedes explored mechanics, hydrostatics, and approximations for pi. So, Greek mathematics emphasizes logical education and proof, a shift from earlier practical approaches. Key figures like Pythagoras, Pythagorean theorem, Euclid as elements, and Archimedes mechanics and hydrostatics by approximation significantly advanced mathematical theory and laid the groundwork for modern mathematics. So the next time you see a geometric shape or use a mathematical equation, remember the ancient Greeks. They transformed our understanding of math and helped us see the world through a lens of logic and reasons. So the fourth one is Chinese mathematics is also under the ancient civilization, and this is the last one as key figures. So 9 chapters on the mathematical art, a compendium of techniques for solving linear equation, volume calculation, and more. Early use of negative numbers. So, or Chinese mathematicals is notably the 9 chapters on the mathematical art showcase advanced techniques for solving linear equations and calculating volumes, and included early use of negative numbers. This period in Chinese mathematics is a testament to the ingenuity and practical focus of ancient Chinese scholars who developed a rich mathematical traditions that continues to influence us today. Now let's talk about the medieval period. Mathematics flourished in India and the Islamic world, while Europe saw limited advancement due to the Dark Ages. During the medieval period, while Europe saw limited mathematical progress, India and the Islamic world flourished. Key Indian contribution included the formal definition of zero and advancement in trigonometry. The Islamic Golden Age saw the translation and expansion of existing knowledge, with significant contributions from Al-Khwarizmi or the algebra, and Omar Khayyam sa geometry. So, Indian mathematics is under the medieval period. Brahmagupta, the first clear definition of zero as a number, development of trigonometric function like sine and cosine. Aryabhatha calculated the Earth's circumference with remarkable accuracy. Ancient Indian mathematics left an indelible mark on the world of mathematics. Brahmagupta's 7th century definition of zero as a number revolutionized the way we understand numbers and paved the way for more advanced calculations. Indian mathematics also developed trigonometric functions like sine and cosine, which are essential for understanding angles and triangles. Aryabhatha, a 5th century mathematician, even calculated the Earth's circumference with astonishing accuracy, demonstrating their advanced understanding of geometry and astronomy. These contributions highlight the ingenuity and impact of Indian mathematics on our understanding of the world around us. So, the second is Islamic Golden Age is also under some medieval period. So, translated Greek and Indian works into Arabic, preserving and expanding mathematical knowledge. Al-Khwarizmi wrote on systematic algebra, introducing methods for solving linear and quadratic equations. Omar Khayyam worked on cubic equations and contributed to geometry. During the Islamic Golden Age, 8th to 13th centuries, mathematics flourished as scholars translated Greek and Indian works into Arabic, preserving and expanding mathematical knowledge. So, the third is European mathematics, the introduction of Hindu-Arabic numbers to Europe by Fibonacci. So, Fibonacci's 1202 book, Liber Abaci, introduced the efficient Hindu-Arabic numeral system to Europe, replacing the less versatile Roman numerals. This pivotal event facilitated the transmission of mathematical knowledge from the East and significantly contributed to the advancement of mathematics in Europe during the Renaissance and beyond. Let's talk about the Renaissance and early modern period. A resurgence of mathematical activity occurred in Europe during the Renaissance, fueled by access to the earlier text. During the European Renaissance, there was a remarkable revival of mathematical activity driven by the rediscovery and translation of ancient texts from the Islamic Golden Age and classical antiquity. So, around 16th century, decimal notation became standardized. Solution to cubic and quartic equations were formalized by Tartaglia and Cardano. The 16th century saw significant progress in algebra and the number representation. Decimal notation became standards, making it easier to work with fractions and decimals. Mathematicians like Tartaglia and Cardano made breakthroughs in solving cubic and quartic equations, expanding the power of algebra and opening up new areas of mathematical inquiry. In 17th century, development of analytic geometry by René Descartes. Calculus was independently developed by Newton and Leibniz. Early probability theory by Fermat and Pascal. Advances in logarithmics by John Napier. The 17th century witnessed a remarkable surge in mathematical innovation with several key breakthroughs that revolutionized the field. René Descartes' invention of analytic geometry allowed mathematicians to study shapes and curves using equations, bringing the gap between algebra and the geometry. Proceeding to the 19th century, this period saw significant advancement in abstract mathematics and applied disciplines. Carl Friedrich Gauss' number theory, differential geometry, and the method of least squares in statistics. Évariste Galois established group theory and symmetry principles. Emergence of set theory by George Cantor. Expansion of non-Euclidean geometry by Lobachevsky and Bolyai. The 19th century witnessed a dramatic shift in mathematics, moving beyond practical applications and embracing abstract concepts. Carl Friedrich Gauss made significant contributions to number theory, differential geometry, and statistics, while Évariste Galois revolutionized algebra with his work on group theory and symmetry. George Cantor's development of set theory expanded the foundations of mathematics, while Lobachevsky and Bolyai explored non-Euclidean geometries, challenging long-held assumptions about space and geometry. These groundbreaking discoveries laid the groundwork for modern mathematics and its diverse applications. Proceeding to the 20th century, mathematics became more formalized and diversified with rapid progress in both pure and applied fields. Alan Turing pioneered theoretical computer science and algorithmism, analysis, and algebraic geometry. Mathematics applied to physics, quantum mechanics, economics to game geometry, and social sciences. The 20th century saw mathematics expand dramatically both its abstract and applied aspect. Alan Turing's pioneering work in the theoretical computer science and algorithmism laid the foundation for modern computing. Pure mathematics saw the development of new fields like topology, functional analysis, and algebraic geometry, while applied mathematics found its way into diverse disciplines such as physics, quantum mechanics, economics, diba? And the social sciences. Period marked a significant shift toward the formalization and diversification of mathematics, reflecting its growing influence on the modern world. Then, proceeding to 21st century, modern mathematics is marked by interdisciplinary applications and computational advancements. Heavy reliance on algorithmism, machine learning, and big data, advancement in cryptography and cybersecurity, mathematical models used in climate change, biology, and medicine. The 21st century has witnessed mathematics becoming increasingly interdisciplinary and computationally driven. Algorithmism, machine learning, and big data analysis are now central to many mathematical endeavors, leading to advancement in fields like cryptography and cybersecurity. Mathematical models are increasingly being applied to complex real-world problems in areas like climate change, biology, and medicine, highlighting the crucial role of mathematics in understanding and tackling global challenges.
So, in continuation to our topic, why study the history of mathematics? So, why study the history of mathematics? Because knowing the history of mathematics is crucial for several reasons, especially in education. Because first, it provides context and meaning to abstract concepts. Second, help students appreciate the practical challenges these concepts were originally created to address, such in trade. Number 2 is in navigation. Number 3 in architecture, as a consequence of understanding how mathematical ideas evolve over time. Number 3 reason why study mathematics history. Number 3 reason is it reveals the contribution of different cultures and civilizations, emphasizing the global nature of mathematical progress. It reveals cultures and civilizations' contribution. Number 4, lead students gain a deeper understanding on the subject's development and its ongoing relevance as a result of digging and learning about the achievements and struggles of mathematicians throughout history. Also, it fosters critical thinking and inspires curiosity, offering students valuable insight in process of discovery and importance of persistence, of which shows how mathematical breakthroughs often emerge from trial and error. So it inspires curiosity, which the mathematical concepts or the mathematics came from long ago, from trial and error. Ang uban, trial and error. So, it inspires curiosity because sila gani nag-trial and error. Number 6, importance of study is the revelation of connections to other disciplines such as in science. Number 2 in philosophy. Number 3 in art. And number 4 in technology, demonstrating its interdisciplinary nature in the historical journey of mathematics. So, the history of mathematics, naagid siya connection sa science. philosophy, art, and technology. Number 7, it enriches students' knowledge and encourages them to view mathematics as a dynamic, evolving field with real-world application, rather than just a collection of abstract formulas. Real-world application. For example, basic example lang for the formulas of mathematics in multiplication. Halimbawa, na ako'y 3 apples. And some of the people as well has 3 apples as well. Tapos, we are 20. So, 20 persons has 3 apples. If combined together, the apples that we have, which is we are 20 persons, how much? Or, what's the quantity? So, in formulas of mathematics, 20 times 3, 20 persons times 3 apples is 60 apples. So, it's a real-world application, not just as only an abstract formula. Number 8. Very relevant today because of the ideas used in modern technology and science came from the past, came from our ancestors, which is, for example, the concept of algorithms, which were first developed in ancient mathematicians and which are crucial for today's field, such as in computer science and digital security. So the algorithm that was developed in ancient mathematicians, so it is useful in today's field for computer and digital security. Also, historical figures work of Newton, Euclid, and Gauss lays to the foundation or the groundwork for the field of physics, engineering, and economics, which are the key to technological world we live in today. Number 9. Helps us understand how the tools we use today were created. For example, calculus was invented to understand motion and change and still used in the fields of physics. Number 2, medicine. 3, engineering. Also, other earlier discoveries lead to many ideas behind artificial intelligence, machine learning, and data analysis. And knowing the history behind the ideas help us to see why they are so important for solving challenges we face today, like health issues, climate change, and security problems. Another reason why need to study is it shows us how different cultures have contributed to the development of math over time. From ancient Egypt, Greece to China and beyond, of which people around the world have shaped the mathematics we use today. So because of the contribution of different culture, which is from Greece, China and beyond, Egypt, so the mathematics that we have today, modern and innovation of mathematics, is from them. 11. It teaches us that math is a shared human achievement and encourages people from all the backgrounds to continue building it. So because the history of mathematics teaches us that it is a shared human achievement, so it encourages us to build and improve mathematics much more. Number 12. Shows how powerful and essential it is in solving modern day problems and improving our understanding of the world. So that's the last reason as well. How powerful and essential it shows us for solving our modern day problems and improving an understanding of the world today. In continuation to our report, so what is Babylonian numerical system? First, we need to define numeral system. So what is numeral system? Numeral system is a system used to express numbers. That's why numeral system, a system used to express numbers. A writing system. Also a set of symbols or characters that represent vertical values, allowing people to perform calculations and present quantities. So numeral system, there are different used through history, different forms, which is, for example, the Roman numeral system, Hindu-Arabic numeral system, which is used as of today, and 3, Mayan and Babylonian system. So what is the importance of numeral system? First importance of numeral system is it forms the foundation of all in mathematics, in science, engineering, and daily life. That's why it is important. It is the foundation. Number 2. Today, the Hindu and Arabic numeral system, which includes the digit of 0 to 9, is a universal use for all types of calculation, measurements, and technological processes. Number 4 reason. Number 3 reason is allows for clear communication of numeric values, as 1 is equivalent to 1 as well. 10 is equivalent to 10. So that's numerical system. Allows for clear communication. So because of numeral system, it is very clear that 1 is 1. Number 4, making it essential for everything from financial transactions, scientific research to computing and digital technologies. Number 5, historically, the development of numeral system marked a significant step forward in human civilization. Because of numerical system, so because of number system, to represent large number efficiently is very possible in mathematics. Number 8, numerical system lays the groundwork for modern mathematics, facilitating the development of algebra, calculus, and beyond as a result of advancement. Number 9. Nine reason. It enables us to express and manipulate numbers. Also plays a key role in our understanding of the world. Express us and manipulate numbers to understand our world. Just like, tagpila inyong bugas. Tag 50 po ang kilo. Just like that. So number 10. Number system is the language of, so the importance of number system is the language of mathematics, science, technology, and shaping how we quantify, the language of measurement, and interpreting data. So the importance of numeral system is it is the language of those. And lastly, the last reason of the importance of numerical system is one reason of the advancement through the need to solve practical problems, and its continued use today highlights its enduring importance across all the aspects of modern life as a result of human innovation of its historical evolution. So Number system is one reason of the advancement in solving practical problems as of today, till today. So, next is, what is Babylonian numeral system? Specifically, Babylonian numeral system. So, Babylonian numeral system is used in ancient Mesopotamia. So, originated from Mesopotamia, the ancient Mesopotamia, particularly Babylonians. One of the earliest known numeral system. So, Babylonian numeral system is one of the oldest known. Also, a sexagesimal system, which is based on 60, as opposite of decimal system, which is based on 10. Babylonian numeral system is significant not only for the use in everyday life, but in the development of mathematics, astronomy, and timekeeping. And the sexagesimal system of Babylonian numeral system is originated with the ancient Sumerians in the 3rd millennium BC and was passed down to the ancient Babylonians, used in a modified form for measuring of time, angles, and geographic coordinates. Also, Babylonian numeral system is the central to the development in astronomy. So because of numeral system of Babylonian, so there is the development in astronomy. Because they use it to create detailed star catalogs and predicts celestial events. Their ability to divide the sky into 360 degrees and calculate the position of stars and planets was a groundbreaking, or the starting point. Babylonians as well create extensive mathematical tables, such multiplication tables, used for practical purpose, including trade and architecture. Understanding of mathematics was highly advanced for their time, especially in solving quadratic equations. So quadratic equations is already existed in Babylonian numeral system, or the Babylonian mathematics. Also, the Babylonian numeral system is an inherited ideas from the Sumerians and from Akkadians. The number system of these earlier peoples came from the base of 60. So the number system is based on 60 again, which is called sexagesimal system. And neither the Sumerian nor the Akkadians, which is they inherit these ideas, the Babylonian numeral system, neither the Sumerian nor the Akkadian system was a positional system. So dili pa siya arranged. But the Babylonians advanced it. Babylonians has positional system, which undoubtedly their greatest achievement in terms of developing the number system. And Babylonian numeral system was their biggest achievement in mathematics, some argues. So when told by the Babylonian numeral system that was based on 60, people's reaction is, wow, a lot of special numbers to be learned, to memorize. P60. Because that's reaction is from our concept of decimal system, that is from 0 to 9. So 10 symbols. But however, Babylonians only have 2 symbols to produce their base of 60 positional system. Babylonians only has 2 symbol. And this symbol, which is positional and is based on 60, also had some vestiges of base 10 system within it. Even though it's based on 60, but you can see it, or imo siyang makita na within itself, na siya base 10. And the 2 symbol is a nail or a wedge symbol, lansang, symbol of nail. And it came from the word koneos, a Latin word sa nail. And that koneos, later, so ang giname nila sa ilahang tablet is cuneiform, from the word koneos, which is a nail, which that nail represents as well number 1, or equal to 1. And another symbol is equal to 10, equates to 10. It's like an angle bracket opening right for the value of 10. It's like an angle bracket opening right. And these two symbols could combine to represent different numbers, which is based on 60. And for the demonstration, here is the examples for the demonstration. So in demonstration of Babylonian numeral system, so this is the two symbols, which is this one and another one. So this one is a wedge or a nail-like form, a wedge or a nail, which is from the Latin word, came from the Latin word coneos. Another one is another symbol, the second symbol is like an angle bracket opening right. So for writing the Babylonian numbers, which is based on 60, so combination of these two to write 60. For example, for number 10, for example, for number 5, because number 1 is already given, value of 1. So for number 5, it's 1, 2, and 3. Then 4 and a 5. That's 5. For 6 is 1, 2, 3. 1, 2, and 3. It is in line, in order, 3 of 3. For 9, so add another for 9. That's 4 for 6. If you add another one, or that's the number is 4, 6, 7, 8. Is 4, 8. This for 6, another 2 for 8. So for 10 is this for 10. Like that for 10. If it's for 20 is 2. If 30, it's 3. 1, 2, and 3. If for 20, so numbers for 20, 24, you copy a total of 10, two values of 10, two values of 10 for 20, and a 4. 1, 2, 3, and 4. That's for 24. If 34, another. Again, for 30, for example, 35. Again, 3. 3 tens. 3 of 10 symbol. And a 5. 1, 2, 3, 4, and 5. That's for 35. So in 40, so the position in 40 is different because it is not line but a triangle shape. For example, 40 is 4 symbols of 10. For 40, it's 1, 10, 20, 30, and 40. So that's a symbol like triangle. For example, 40. Example for 44. Yes, 44. So the symbol is, you copy this symbol. 1, 2, and 3, and a 4, and add 4. this? 1, 2, 3, and a 4. Fourth 4. For 50, 50. Goes like this pa rin. Pero, it's 10, 20, 30, 40, and 50. That's for 50. For example, for 50, 58. So you copy the symbol. 1, copy like this, like 2, 10, 20, 30, 40, and 50. For 8, like this. 1, 2, 3, 4, 5, 6, 7, and 8 for 50. So that's how Babylonian numeral system is demonstrated.
For our recap, here is a full illustration of the Babylonian numeral system, which consists of the values from 1 to 59, which is converted from and to the base 10 to the base 60 of Babylonian numeral system. You can see the symbols here, which basically has two different symbols merged or meshed together in order to create a symbol that is a symbol like that is greater, or that has more than one or two mesh or merge of symbols. Like from number 1 and number 10, you will see that these are looking like a wedge or a nail for the 1, and then number 10 it looks like an angle, but when it comes to the 20, it is just still an angle, but it's now 2, and until it goes to 3, 4, and 5, it looks like it has been stuck together in order to form that specific structure. The Babylonians wrote their numbers in this way using cuneiform, which is the clay tablets that they use in that era. So the numerals themselves were represented by the two basic symbols, which is a vertical wedge and a corner wedge, which values 1 and 10 respectively. So if you notice, the Babylonian system is a positional, which is similar to the modern decimal system, which means that the value of a symbol depends on its position. So if something is a first place, then it will be counted to 1. If it's a second place, it will be counted to 2. Not all numerals are like that. And it's because, like, for example, if you joined a certain competition and somehow you end up being in the third place, if you're awarded with that, sometimes you will be called as the second runner-up, but sometimes it will be a third place. So not all ranks or are in position will be in the same value. So if doesn't mean that you are second, it means that you will be said as a second place. Sometimes you will be said as the first runner up, because the first one really to the competition is called the champion. So the champion is the first rank, while the first runner up is the second rank. But the second rank isn't the second runner up, but rather the first runner up. That's all. Now let us proceed to an important part of this lesson, which is solving problems, or rather conversion of a base 10 number and the basic C Babylonian numeral system, which is also can be done in vice versa. But before that, we will start in here first. So We already know that it has two symbols. Babylonian numeral system has two symbols, which is meshed together or to create another values of numbers. So the one place here will be simplified in drawing as well as the 10th place in order for you to not have a complicated time in solving problems. And by the way, what we will be talking about here is from a reference video from someone who uploaded on YouTube, which is named as Ted Hogson. Credits to Hogson, and the link is just above this template, which is entitled The Babylonian Numeral System, that shows how to convert a base 10 to base 60 and vice versa. Since we are converting here, you can also say that we are solving a problem, right? And in solving problems, we still have to know the numbers. And if you notice that that's two symbols of the Babylonian numeral system only has 1 and 10 just merged together. But what about 0? In this case, the 0 that we are going to use in case you are going to experience a 0 in a conversion would be a placeholder. And a placeholder looks like triangle in this case, as stated in the video. So this placeholder is equals to 0. Now let us move on to the important details. We are going to take note that this is a base 60 system. It means that we are going to use the numbers of 60 or the multiples known as squares multiples of 60. So when you say 60 cube, it means they are 360s multiplied together. So 60 times 60 times 60. You should take note that the value of that is 216,000. And the 60 square, or the below exponent before a 60 cube, is equals to 60 times 60 is equals to 3,600. The next one will be the 60 to the 1 exponential power, which basically is also equal to 60. And the 60 power, or the non-existent 60, would then be equal to 1, since if you have exponent of a number, if you have a 0 exponent of a number, it means the answer will always be 1. It is a part of the math rules. And here we are to example number 1 from a reference that we have in a YouTube. Credits to Tom, the YouTuber. So in example number 1, we shall convert the following Babylonian numbers presented here in the presentation and convert it into a base 10 number, or the number that we are currently using, right? Now, you will see that these Babylonian numbers are grouped into sets. And you will see the red marks here, which is the 60 cubes, 60 squared, 60 ones, and the ones, meant that they are meant to be grouped together in order to find this base 10 number. So this is a basic system. The first that they used was a 60 cube, or the leftmost part is presented as a 60 cube, or 60 times 60 times 60. After that will be the 60 squared, or the 60 times 60. The other is a 60, and the last one would be the ones, which is equals to 1. Now for the first set, how many tens of, or symbols of tens can you see, and the ones can you see? So you will find out that in the first set, or the leftmost part set that is grouped in the 60s, 60 times 60 times 60 times 60 place, it has 2 tens and 1 1. It means if you add them, it will be 10 plus 10 plus 1 results to 21. Now that 21 will be multiplied by the 60 power of 3, which is in the leftmost part. So this is the rule when converting. 60 times 60 60 times 21 will be the first answer, but not yet the final answer. So after the leftmost part set, now we have here another set, which is the second set. But it's a placeholder, which means that if it's a placeholder, it means it's not 1, it's not 10, nor any value more than 0, but rather it is 0 because it's a placeholder. So the 0 will be multiplied to the 60 times 60, or 60 squared, which result to 0. And Here, after that will be the third set, which is part of the 60s, or the 60 with the exponent of 1. This exponent of 1 will result to 60. So 60 will be multiplied to the value of the Babylonian number in the third set, which is, you can see here, there are 3 tens because there are 3 angles, and 6 ones because there are 6 triangle-like shapes. Then after that, the fourth one will now be multiplied to 1. The fourth set will multiply 1. The values for the fourth set will be, there are 4 tens because there are 4 angle-like structures, symbols, and for the ones place, there are 3 ones because there are 3 cone-like structures. So it will be 40 plus 3 equals 43. Now, add all their sums. So 21 times 60 cube, then the sum will be added again to the 60 squared times 0, and the sum after that will be added again to 60 times 36, and the sum after that will be added again to 43 times 1. The result is 4,538,203. So this is the base 10 number of the converted Babylonian number. But what if it's reverse? What I mean to say is, what if the example would ask you to convert from a Babylonian number to a base 10 into a base 10 to a Babylonian? This seems quite complicated, and the difference is that it will have a different method of solution, but we'll see on how it will be done. So it is from the same YouTube reference, thanks to the Curtis and thanks to the owner of that video. Here is a second example. Convert the following base 10 number to a Babylonian number, and then the base 10 number is equals to 1,160,207. We have to take note, always take note in the base 60 system of the 60 times 60 times 60, 60 times 60, 60 and 1. So the 60 cube results to 216,000, the 16 squared results to 3,600, 60 will be equal to 60, and 1 will be equal to 1. So if you memorize that one, it will be easy for you to answer this second example. So let's move on to the solution. The number that we are going to convert, which is 1,116,3207, is to be divided by the first base 60 set, which is equals to the 60 cube, or results to 216,000. So the division of the two numbers will result to 5. It result to 5, and it has a remainder. And that 5 exactly will be in the first set, or the leftmost part set of the Babylonian number that we seek to find. So to draw that, we have the first set to have a value of 5. So it means we can draw 5 ones in the first set. Now, after that, we still know that there's a remainder of value after dividing the number 1,163,207 to the 216,000. So the remainder after that is need to be found in order to get in the second up to the fourth set. So to find the remainder, the 1,163,207 would be subtracted to 216,000 times 5, and it will result to 83,207. This 83,207 will now be divided to the 60 times 60, or 60 squared, and the answer for that would result to the value of the Babylonian number in the second set. So 83,207 divided by 3,600 will be 23, and it has another remainder. So the same process for the first set, 23 times 3,600 will be, the result for that will be subtracted from the 83,207, and the remainder is 407. So for now, the structure that we have made is, first is the 5 ones. The 5 ones in the 60 cube leftmost part. Then the next one is a 23. The value of 23, which is illustrated in 2 tens and 3 ones. So this is the second set. Now after that, we still have a remainder of 47, which now then be divided into the third set. So 47 divided by 60 will result to 6 with a remainder. Now, same process again. After knowing that process and figuring out, the answer of the remainder will be 47. And lastly, for the last set of this, in order to find the one set, we know that the remainder is 47. Thus, the fourth set of symbols values to 47 itself, which is equals to the 4 tenths and 7 ones. That's just how easy it is to convert a base 10 to a Babylonian number. You just have to divide the biggest ones, and find the remainder. After finding the remainder, that remainder again will now be divided to the 60 square. And once again, after putting down the second, the remainder of that after that will now be divided again to 60, and the remainder of that again will now be divided into ones. That is all on the process on how to do that. The relevance of the Babylonian numeral system. The Babylonian numeral system was one of the earliest and most advanced numeral systems in the ancient world, which originates in Mesopotamia, right? And we believe that the legacy of the Babylonian numeral system will extend and forever extends beyond timekeeping and geometry. Like in modern day geographic coordinates like degrees, minutes, and seconds of latitude and longitude we still be using and is still seen as of today. These are also based on sexagesimal system itself. Similarly, calculations that involves angles in trigonometry and geometry also still relies on this 360-degree circle, which is a system pioneered by the Babylonians itself. These contributions will forever demonstrate the enduring influence on their mathematical innovation and influence, which it continued to shape many of the systems that we rely on in everyday lives until the end of time. In conclusion, the Babylonian numeral system was one of the most sophisticated and influential mathematical systems of the ancient world. It is also advanced in such areas of mathematics, and this influence is a testament to the lasting impact of ancient mathematical achievements on the understanding of our world today.